Keplarian planetary dynamics, the third law states the square of the orbital period will be directly proportional to the cube of its semi-major axis. It could be apogee and perigee. So I'm going to provide a proof and derivation of the third law, which is quite simple, straightforward, and rooted in arithmetics, and there's no differentiation or integration involved. First, we have to realize that the formula for escape velocity, which I mentioned in many of my previous videos, is whole under root 2 times gravitational field constant times the radius of the planet. So this will give you the value as to how much velocity is required to escape any particular planet based on g, because g varies per planet. The second formula you need to realize or understand is when trying to quantitate the velocity of a planetary body, you use v equals uppercase G, which is a Newtonian gravitational constant, which is not the G field quantitation. This is the gravitational constant derived by Newton after a lot of complex mathematics, which he was very good at, and is available from Principia Mathematica Volume 2. And so gravitational field constant, which is 6.667 times 10 to the power minus 26 newtons per meter squared, something like that. And you'll multiply with the mass of the planet, and then divide it by the radius of the planet, whichever planet it may be, and then whole under root. Now, when you have a SATCOM system like a geosynchronous or geostat satellite orbiting the Earth in an radial, either polar or equatorial fashion, or is geosynchronous by locking the coordinates with the planet, then you use this particular formula, which is, and if you want to know the velocity of revolutions per unit time, you'll have to use 2 pi r divided by t. So this is what you use, and t is usually every 24 hour, so a 24-hour period. The other thing you need, and so then what you do is you can just you could derive the K3 just by equating equation two and 3. That's pretty much it. So we'll equate equation 2 and 3 together. So the velocity, so it would be gm and then when you square both sides, or you take the root off, one would stay plain and the other one would get squared. So if we square both sides, I'm going to do it in one step. There's no need for rewriting it and squaring it again. It'll be, but this one would get doubled. So you can see we are reaching a point where square of the orbital period shall be directly proportional to the cube of the semi-major axis. It could be apogee or perigee. And then just switch and swap. T squared over r cubed is 4 pi squared over gm. That's the mass of the planet. We have we have in every equation we'll have this. We'll have at least this. So those of you that do gravity calculations on a regular basis, you need to have the product of 4 pi times g in your pocket. Just write it down somewhere, and it should be, I think, sorry, is it sorry, minus 11. My is minus 11 newtons meter squared per kilogram squared, and you'll see that it'll come out to be 2.6, so it's 10 to the power minus 9 something something. So just remember this, or you could write 2.63, and every time you're doing these calculations, sorry, it was supposed to be divided, sorry. So 4 pi divided by 6.67 minus 2. Yeah, so this will be 5.92 times 10 to the power 11. Just remember this number, so whenever you're doing these calculations where K3 is involved, just plug this value in, divide it by the mass, and then multiply or divide it by one of these values, whichever you require. So that'll be so just remember 5.92 times exponent to the power 11, and you just have to do that, and that's it. So this is your proof. Equate the two velocities and square it, remove the under root, swap and switch, and just remember this, pocket this value for future use, and that's pretty much it. You're set to go. Very, very simple and entertaining bit of Keplarian planetary dynamics. Thank you very much. Cheers, take care, bye now.